referred to as a linear power supply, right? So y'all got any questions on that? So what's the main units of a linear power supply? And what's the function of each? Nobody knows. Right. And then we usually have a transformer too. And what does the transformer do for us? Well, literally you could step it up, but it all depends on what the requirements of the load. But the transformer basically sets the voltage for the load. We regulate off what the transformer does, right? Understand? Does that make sense? So normally we have a transformer. And what does a transformer do? And a lot of people will say it steps the voltage up and steps the voltage down. But it does a lot more than that. What don't it change? Yeah, it don't change power. So power in and power out are the same, right? Or close. Depends on the efficiency of the transformer, but most of our transformers these days are well over 95% efficient. So for approximations, and we do a lot of approximations in electronics because it's too hard to do the actual dynamics of what's going on, right? You understand that? So the transformer, when it steps the voltage down, then it's going to require more current to produce that power. When it steps the voltage up, it's going to require less current to do the power, right? And of course, so this is the parts, but we got to remember that odds are there is going to be a transformer right in here. And this is what we call a linear power supply. The other type of power supply we have is what they refer to as a switch mode power supply. Let's see if we can find a block diagram of a switch mode power supply on the internet. Oops. So here's what it says, the switch mode power supply block diagram. So this is where we start getting into more complicated circuitry. So this is kind of backwards. Notice what they do. They start off with a rectifier. So they take the input, don't send it to a transformer. They don't care what AC you got. So if we got 120 volts, then we're going to get 120 volts out of that. And then they bring it into what they refer to as a pulse width modulating oscillator. An oscillator is a device that takes DC and converts it back into, not necessarily AC, but converts it back into a pulse stream or a AC cycle. But it's called pulse width modulation. I'll show y'all that in a minute in the scope. And basically what the pulse width modulation is doing is it's opening and closing the switch. But the opening and closing the switch is a lot faster than what Alabama Power generates, usually 20 to 50 kilohertz. Then we have our what? Yeah, then we have a transformer. But you got to understand one thing that I teach and I push all the time is we call this a electromagnetic, or we call it an induction or induced voltage. We call it electromotive force. Have y'all heard of that term before? Well, you need to, because a lot of big books teach electromotive force instead of voltage. Because one thing they don't like, we got current, And in formulas, we got current, right? You understand? And we come up here and we say, okay, I is equal to V over R, but I uses the watt unit. I uses the unit of amperes, right? You understand that? And of course, R is equal to V over I, and the unit is the ohm. Now, V is equal to I times R, but the unit is the volt. So you got V is equal, and your answer is D, right? So it doesn't look mathematically correct to have V on both sides of the equation when we do this. So another name for voltage. So that's why we say voltage is equal to, not volts is equal. Voltage is equal to I times R. And then the unit's that. But another name for voltage is an electromotive force. And we refer to it as an EMF. So a lot of books teach E is equal to I times R. You'll see that all over the place. So electromotive force, an EMF, is another name for voltage because that's what it is. It's an electrical force, right? You understand that? So this is something you got to get used to because you're going to see this formula a lot. You can say, give me the formula, Ohm's law, and you'll see just as many E's as you do V's. Now, one of the main methods, and we can create electromotive force several different ways, but one of the main ways that we produce it is through, so we can't create energy. Y'all understand that? What can we do with it? We can change it. We can change it, right? You understand? So we can take gasoline, which is a form of energy, and we can put it in our cars and we create rotary motion out of the power, right? But the power that the gas generates that consumes is always going to be a little more than the consumed energy is always a little more than what we actually produce. To produce a EMF electromagnetically, we need a magnetic field. Oops, see if I can spell magnetic right. And we need a conductor. And we need what we refer to as relative motion. So magnetic fields create energy, right? What does it do? It either repels or attracts, right? You understand that? So what happens if I've got a magnet and I got one or two things? I can move the conductor, and when it cuts through those magnetic lines of force, it produces a voltage in that conductor. Or I could just as well come up here and have a conductor sitting over here, and I could move the magnetic field across the conductor. And either one of those would produce an EMF into that wire, a very small wire. But if I come over here and start taking my conductor and I start putting it into a coil, and then I swing the magnetic field through that coil, then what happens is when it goes in this direction, it would basically produce all these little tiny cells, but they would be in what we call series 80, which means their voltages would add together. Y'all understand that? And then, of course, when it goes back the other way, then it would all that happens is the batteries would just change polarities. So what determines the amount? Number one is this energy generated by the magnetic field. So the three things that determine the amount is the strength of the field, it's hard to write on something that's bouncing. Then, of course, we say the number of conductor coils. And the third thing is what Courtney said is the speed of the motion. So if I can spin a conductor through a magnetic field, so if I'm spinning it like this, that means it automatically generates alternating current. Generates AC. And every time it swings past a north-south pole, so we can put multiple poles on there, right? You understand that? Multiple magnets. And we get one cycle for each when it goes past each pole. So the more poles we have, the slower the generator can run and produce that frequency. So if you ever seen the big generators at Alabama Power, it don't look like they're moving too fast, but they got a lot of magnetic poles. And what we said we can move the conductor through the magnetic field, or we can move the magnetic field through the conductor. Another thing that we can do, and I know y'all understand electromagnets. Y'all okay with electromagnets? Y'all know what electromagnet is? You okay, Courtney? Okay. What advantage? So this could be a permanent magnet, or it could be an electromagnet. What advantage does an electromagnet have over a permanent magnet? You can control this right here. Control the strength of the field. We can turn it on and off, yeah, which is great. I mean, so now when you get out there and turn your car off, the alternator is off, right? Understand? If we turn our car on, then the alternator is allowed to work, but we still got to have what? Well, what's nice about this is that you're not out there rewinding your alternator. And the problem we have with a car is that the speed of the alternator is constantly changing. It's not on a constant speed drive. It's hooked up right up to your motor, right? It's got a belt out there. And when your motor goes faster, the alternator goes faster. When your motor slows down, the alternator slows down. So what would be happening is that the output of your alternator would be all over the place. So if we didn't do something, you know, when I cranked my car and it was idling, my lights or nothing would work. And when I got up to 80 miles an hour, everything would burn up. But what do? What do they control? Well, your regulator controls this right here, right? You understand? It controls the strength of that electromagnet. So it's spinning an electromagnet out there. So if the output of the alternator tries to go down, your regulator raises the strength of the field, which causes your output of the alternator to go up. If it tries to go up, what does it do? It decreases the strength of the field and causes your alternator to regulate, and it's doing this instantaneous. So that's regulated voltage. So that's what your regulator does. And by the way, what your regulator does is it spins the magnetic field, but it spins an electromagnet. So the rotor is an electromagnet, and they pass the electricity into the rotor through what we call slip rings. So there's two copper rings on the back of the rotor. You can't see them. And then there's brushes riding on that rotor. But why we like to spin the magnetic field is you're not pulling the actual output of the generator off the rotating part. You're pulling the output of the generator off the stationary part, right? Which we call a stator. Well, with transformers, to determine what we get with transformers is what determines the amount of EMF we pass from the primary to the secondary. The turns ratio. But what we see is the higher the frequency, the smaller the number of turns could be, not necessarily the turns ratio. So I'm over here and I've got a 2 to 1. So over here that means I might have 1,000. Over here I would have 500. Right? You understand that? But what you got to do is you got to consider what we call the X of L and the X of C of the X of L of the transformer. So the lower the frequency, the bigger the transformers have to be. The higher the frequency, we get more motion. The transformers become more efficient, which means now we can limit the number. We can drop the coils of wire down over here we might have 10, right? And over here we might have 5. If we can run it at a high enough frequency to make the transformer very, very efficient. So one of the biggest advantages of a switching transformer is that the size of everything goes down, because now the transformers become really, really efficient because you're at a such high frequency. So the transformers are little old tiny things. They're usually round transformers. They call them, I forgot what they call them, radial transformers or something like that. Your filters don't have to filter as much, so the filters can be really, really small. So the advantage of a switch mode power supply is all the components are very small. So that means the power supply itself can be what? Can be real small. Linear power supplies have got to use these big old transformers because the frequency is so low. To get that efficiency, they got to use a lot of turns, right? And they got to use a lot of copper. Now, what determines the current rating of the transformer is the size of the conductors. So when we talk about this, notice there's nothing in here about the current. So how much current you can get out of a generator, an AC generator, is the size of the wires they use inside there. So a lot of people will say, what determines the amount of voltage you can get out of an alternator? A lot of people say, well, the size of the wire. Well, the size of the wire has nothing to do with the amount of EMF you get out of there. It's just that if you use real small gauge wire, if you tried to load the alternator, the voltage would drop down because the wire would have so much resistance, right? You understand? So there's a lot to the designing of that. So this is the way transformers work, and this is why they only work with AC. So when I come over here and demand a load, it's going to demand a current over here, right? You understand that? At a certain watts. Well, how am I going to pass the energy from the primary to the secondary? Well, the strength of the magnetic field is going to be determined by the current demand of the load. Does that make sense? And I'm not getting in there and rewiring my transformer while it's running. So, but we got to have what? We got to have what? We got to have motion. DC doesn't have motion. So that means transformers only work with something that's changing, right? You understand that? So transformers work with AC. Which hopefully that makes sense. But on a switch mode power supply, so what do we do on a switch mode power supply? Well, the first thing we do is regulate it to make DC. What advantage does DC have over AC? Huh? Well, what is the advantage of DC over AC? If there was no advantage, guys, we wouldn't have DC. If there's no advantage of AC, we wouldn't have AC. Technically, maybe yes, but that's not the main reason for using DC. So we can do this with DC. We can electronically control DC. So anytime when I'm talking about electronics, we're talking about what? DC. So this computer does not operate off of DC. This computer does not operate off of AC. This guy doesn't operate off of AC. Those robots over there don't operate off AC. They are DC devices because we need to electronically control them. Your TV, your radio in your car does not operate off of AC. It operates off of DC. So somewhere down the line, we got to have what we call a power supply, right? A DC power supply. So this has got batteries in it, but it still operates, but batteries generate DC. So what do I have here? What's it? It's a power supply. What's it doing for me? Here's AC. Here's what? DC. So all your electronic devices has a what in there? Power supply. So the big advantage of DC is we can electronically control DC. AC is real hard to electronically control. It basically wants to do what it wants to do. Right? You understand? So once we got 60 cycles from Alabama Power, we can't do anything about that unless we convert it to DC. Back to what? Back to AC. And that's basically what we're doing with this switch mode power supply. It's not real AC. But so what they're doing is they're coming up here and switching off on real fast. We bring it into the transformer. The transformer is a little old tiny thing. Then we run into what? Rectifiers and filters. But then we have this thing called feedback. And what the feedback does is it comes up here and controls the pulse width modulator or oscillator, which sets the output voltage. And this is the problem we have, is this feedback loop. Most of the time when you get it, we get it what we call into a troubleshooting loop, where everything measures what it's supposed to measure, but the thing don't start oscillating. And so the biggest problems we have with switching mode power supplies is that they're hard to troubleshoot and hard to design too. And another problem you have is they generate tons of electrical noise. They're very noisy. They create bad power factors. Are we okay? So I'll have to add a little more to my little thing. By the way, the primary filtering in a linear power supply is capacitor. The primary filters used in a switch mode power supply is inductors. So who we missing? Brandy's not here. Kareem's not here. And I still hadn't added that other formula to the formula sheet. That 90% thing, that is so cool. I really like that. So let's look at just a little bit at the filter before we go to lab. So what I've got, this is full mode. This could just as well be half wave, but this is full wave. And what we get out of our rectifiers, we get what we refer to as pulsating DC. And of course, we get an average out of this. So that's what your devices would do. It would average that out, right? And if this is full wave, then our DC average is equal to 2V peak over pi. And if this was half wave, our DC average would be equal to V peak over pi. Okay. So what I'm trying to do is I'm trying to get rid of this and, of course, raise this average up. So what does your car use for a filter? You don't see any big capacitors or inductors out there. What does your car use for? Well, rectifiers is not filters. So you're right, rectifiers. But if I was to go out there and all I had was a rectifier, this is what I get right here. If it was single phase. Now this is another advantage of three phase. So if I use three phase, let me find another blank sheet of paper. I thought there was one back here at the front. Oh, there. So three phase, what we do is it takes three conductors and we generate phases that are 120 electrical degrees apart. So if this was the first phase, phase A, then phase B would start 120 electrical degrees, which would be right around here. And then it would come up and cross this one right here. And then it would drop down. I'm trying to do this, guys. And then it would come up. And then phase C would come up. And it would start 120 degrees right here. And then it would come up. And then it would drop down and look like that. So I tried to draw one cycle this waveform, but you got to understand these guys are occurring constantly. So this was 3-phase. It's pretty good. Well, what's going to happen when I half-wave rectify this thing? Well, if I halfway rectify it, what I get is I get this. Because that would take this one, right? You understand? That would be one of them. And as soon as it drops down, we would have this. And as soon as it drops down, we would have that. So this would be 0 down here. And what we'd get is we'd get this. Now this is DC. But it's not regulated DC, right? You understand? Now what would happen if we full wave rectify it, which means I'm going to take this negative alternation and I'm going to come up here and I'm going to stick it in here. So what we get on full wave is we get pretty good DC out of 3-phase. If we full wave rectify it. And all it takes, so a full wave bridge would take 4 diodes anyway. So all I'd have to do with 3-phase is I would come up here and add one more set of diodes. And then I would bring my 3 phases in. So this is phase A. This right here would be phase B. And this right here would be phase C. And we would get pretty good DC out of this without filter. And now most car alternators are 6-phase. So that means your rectifiers, you're going to have 3 more groups out here, right? You understand that. And instead of being 120 electric degrees, they're all set by 60 degrees. So when you full wave rectify it, we would get, our pulses would be 30 degrees, and you get pretty good DC out of a 6-phase rectifier. Alabama Power or power companies here generate 3-phase, single phase or 3-phase. There's no such thing as 2-phase right here. Okay, this makes sense? But we still need to filter it some for my stereo. So we use this big old thing right here. We just put it across one of these big old things right here. Right? 1, 2, 3, 4, 5, 6 cells out there. Each cell is putting out 2 volts. And by George, when it tries to go above that, it's almost working into a short circuit and the battery runs it. So your battery on your car, your battery is your filter. Batteries make good filters. They're expensive, but they make good filters. Okay, understand that. But I don't have a battery on this guy right here. So we've got to come up with another method of filtering. So what we're trying to do, so that's 3-phase. That looks pretty good, right? So yeah, these big power companies like U.S. Steel and stuff like that, you know, they want DC. Of course, they use real high voltage DC, but they just come right off the line and rectify right off the line. When we was out there, all the cranes were DC cranes, and they ran off of, I think, 440 DC. So what we do when we get this, if there was some way in the world I could fill in these gaps and have something that basically acts like a little tiny battery and is capable of storing a charge, and then when this drops down, then that device, as soon as it drops down, it would run the load, and then it would run like a battery. So it runs the load, but it's not a real good battery, so it discharges pretty fast. So we would end up with something that looks like this. Now this slope right here, so we use what we call a capacitor. So what I would do is I would come out on my, so first of all I'd have my rectifiers, right? I'd have my transformer, let's put that. And then I have my rectifiers. And then we have filters, and the most predominant filter used in linear power supplies is capacitors. And as soon as they put that capacitor in there, then this pulsating DC is gone. And we turn into this. So the rectifiers are still generating pulsating DC. Y'all understand that? But as soon as we filter it, then the output comes up. And we end up with this. This up here is referred to as a ripple voltage. And what determines the amount of ripple voltage, how steep this thing right here, is the current demand of the load. Understand that? So if I was going to hook this up, and all you're going to do in the unregulated power supplies is you're going to put a capacitor across. I showed y'all that the other day, right? So we'll come over here and we'll have our transformer, and we're using a center tap transformer. That's what the trainer gives us. So we got two options. We can ignore the center tap and hook up a bridge, or we can use the center tap and we can have a power supply. Oops, short circuit, guys. You've got to be careful. If you do this, both these diodes are turned on. And if you got both those diodes turned on at the same time, you have a short circuit. So that's not good. And then we'd come up here and you take the cathodes and hook them together, because this is a positive power supply. And then what we do is we'd come right here and we would put our filter back. And then our load is going to be out here. So what we're going to do is we'll just put a load out there. We'll put a resistive load. Now, capacitors are rated in two things. Anybody know what capacitors are rated? Well, actually rated in three things. The third, of course, would be the tolerance. So what's the other two things that a capacitor is rated in? So what do you mean by size? That's a big word. So is it physical size or? Huh? Yeah, so it's rated in something called farads. And this gives us the storage capability of the capacitor. So the more farads we have, the more it can store. And then we have what we call a voltage rating. If you exceed the voltage rating of these capacitors, especially to reduce the size, what they do is they actually polarize the plate. So these guys are usually used in DC, and we call them electrolytic capacitors. And we do have some smaller ones called tantalum capacitors that are smaller, but they cost a lot. They're smaller per farad, but it's in process. That's not, I didn't want to do that. I wanted to bring up the camera. Get this right in there. Man, I think it's pointing at the wall over here. So to reduce the size of the plate, one plate wants to accept holes, the other one wants to charge electrons. So the plates are actually polarized. And what you see on these electrolytic capacitors is one of the leads is going to be identified. So this one right here is identified as the negative lead. So in DC, it means you better put this guy. Now, normally, this is not always true, but most of the time true. If something has a polarity, it uses what we call a radial lead. So a radial lead means that the leads come out one side. So this is what we call a radial lead capacitor. And the other one is what we call an axial lead capacitor. So it comes out the ends, and it looks like, and it got that name, I guess, because it looks like an axle. Okay, does that make sense? So this is a radial lead capacitor. Now, radial lead capacitors, what they usually do is they make one leg shorter, and this is the negative side. But as soon as you clip those off, they're gone, right? So they also come up and put a designator on here that identifies the negative. For some reason, why they do that, I can't tell you. Normally on a radial lead capacitor, they identify the negative lead. On a actual lead capacitor, they identify the positive. The first thing you're going to do is look for a sign. If you put these suckers in there backwards, and there's really, the only thing that's protecting this thing is the resistance, the DC resistance of the transformer. And it doesn't have very much. You put this in there backwards, guys, this guy's going to swell up, and a lot of times it pops on. So there's two things that you can pop these capacitors, these electrolytic capacitors, these polarized capacitors, if you put it in a DC circuit backwards, or if you exceed the working voltage. Both of them. And I got a video I showed you where these guys are deliberately blowing up the capacitor. And they do two things. One time they blow it up by exceeding the working voltage. The next time they blow them up by doing what? Putting in the circuit backwards. So you really need to understand this. So if you can't understand your diodes, you need to get a dang meter out and figure out what the polarity is you're putting these things in, right? So if you put them in there backwards, they act like a resistor. And if they act like a resistor and you got current, then current flows through it. When they act like a capacitor, there's technically no current flow through it. So capacitors don't do electrical work. They appear to do work, but they don't do electrical. Because the current flow is in and out of it. It's not through it. If you put it in there backwards, current flows through them. Now you got a voltage drop, you got current, you got I square R, you got power, and they get hot. And they're sealed up. The electrolyte that they put in there is a liquid. So that means it's going to start expanding real fast, right? You understand? And it does it extremely fast, and it pops. So if you fill a capacitor and the capacitor is physically hot, then the capacitor fast. Capacitors don't get hotter than the surrounding temperature or the ambient temperature. If you see them and the top is pushed out on them, then that's not good at all. So the top should be really flat, or the end should be flat. The seal down here, this is a rubber seal. It should be seated real good, right? You understand? So this guy right here is 1,000 microfarad, and then it's rated at 50 volts. So if we charge this thing up above 50 volts, between the leads, that's bad, right? You understand? So we call this a radial lead capacitor, 1,000 microfarad. And you can get these all different sizes. The bigger the size, they have some filters. Some people put these things on car stereos. So if you're into stereos and you put these big power amps in your car, the problem is there's not much room to mount the power amp in your car. So where do they usually put the power amp at? In the trunk. Where's your battery at? In the front of your car. So you got to get all this 1,000 watts of power from your battery back to your trunk. You know, you don't want to use, double aught wire to run that back there. So what they do is they use a smaller wire and they put a big old capacitor back there to filter. So when the wires start dropping voltage, the capacitor can run the load for a short amount of time while that base is pumping. Or you could put a big car battery back there too. That would work. So how do we size this thing? Well, so what happens is that when this thing goes positive, then of course at that first instant what would happen is the capacitor is going to charge. And it's going to charge basically instantly. Because the only thing that's limiting the charge rate is the DC resistance of the transformer, and it's got almost none. And that's why these big old diodes, like the 1N40,000 series, they have a surge current of 30 amps, even though they're rated at 1 amp. So they can charge these big capacitors no problem. Now, once we get up to here, and as soon as this drops down, as soon as this drops down like this guy right here is charged up here, the diode's cut off. Because now they're reverse biased. And what happens? So your diodes are turned off all the way down through here, but what happens is that capacitor comes up here and runs the load. So your diodes are only conducting for a very, very small amount of time. But when they're conducting a lot of current, but it don't care because these big old rectifier diodes can handle this surge current, right? You understand? And how long will it would run it? Well, it would run it to the next next peak comes up, and then what does it do? It charges it up, then the diodes, so the diodes are what down here? They're off. So the only time they're on is from here to as soon as the diode reverse bias. So what we would do is we would get a pulsating, we would get a DC out. This is no longer a pulsating DC but it is definitely unregulated. Because this discharge time is basically controlled by the load current. So the more current that the load requires, the faster the capacitors are going to discharge. It's just like your cell phone. So if you stick your cell phone in your pocket all day long and you don't talk to anybody, you don't listen to any music, you don't play any games, your battery will probably last you at least all day, right? You talk on your cell phone a lot and you play games a lot and you get on Facebook a lot or tweet a lot, then your battery runs down real fast. Because why? You're putting out a bigger current demand on your battery. So that's what this capacitor is acting like. It's acting like an extremely small battery that we charge up and then it discharges. Well, what determines how fast it discharges? Well, it's determined by the what? By the load. So we have a capacitor in the DC circuit has something that we refer to as a time constant. And y'all that's had DC, what is the time constant for a capacitor in a DC circuit? How many have had AC? Well, what is it? It's a math formula, so I'm saying equals to 63.2, or about 62%. So what's the formula? It's called an RC time constant. So we can come up here and we can calculate how much it takes to charge the capacitor, and it charges in a loop too. But this charge is not full charge, it's 63.2%. And then during the next, then it would keep charging, but it would charge 63.2% of what's left. And what it's trying to do is trying to charge up to the applied voltage. So the bigger the capacitor, the slower it charges, or the bigger the resistor, the slower it charges, right? That makes sense. And then it would be 63.2% of what's left, then it would be 63.2% of what's left. Then it's 63.2%, but it's going to come up here, starts off charging real fast, and it's going to load over, and soon it's going to get up here. And full charge is considered to be 5 time constant. So to fully charge a capacitor, the formula is time is equal to R times C times 5. But we're not concerned with that. Because we're going to charge this thing. We're not worried about how fast it charges. We're worried about how fast it discharges. And we're never going to get down to 63% anyway. So calculating this ripple voltage, we can come up here and use this formula right here to calculate the amount of ripple voltage. T equals R times C, or CR. Usually we call it, most people call it an RC time constant, even though mathematically it could go either way, right? So I got to get voltage into the formula, because that's what we're trying to do. We're trying to calculate the ripple voltage. So how can I get voltage into that formula? T is equal to R times C. Anybody got any idea? Y'all know when two things are equal to each other, that means you can substitute one for the other. So what I'm going to do is, I got that thing called R in there. And we have a law of electricity that says R is equal to something. R is equal to what? No. Current times the voltage is R is equal to, yeah. So that means I could come in here and I can come over here and I can say, okay, first of all, let's rearrange this one and solve for time. Well, let's do it this way. So I could come over here and I can say, that's still legal, right? Y'all understand that? Y'all understand why? So that's where your power, that's where our three power formulas come from. Our main power formulas, power is equal to V times I. That's power. But then we got power is equal to I squared R, and then we got power is equal to V squared over R. Well, where did these guys come from? Well, they came through by substituting Ohm's law into what these other values are equal to. Right? You understand? So if I come up here and I say P is equal to V times I, so P is equal to V times I. Well, what's V equal to? Well, V is equal to I times R. So I can say V is equal to I times R times I, and that still calculates power. Well, I times I, so that means P is equal to what? I squared R. So that's where these other formulas come through. I squared R, V squared over R, is we just took what these other quantities, what Ohm's law says these other quantities are equal. Okay, so now I got V, I got I got C. But we're trying to calculate V. So what do I need to do? Because what we're trying to do is we're trying to calculate this voltage right here. What do I need to do with that formula right there? So V would equal to what? Well, math experts. Y'all understand why we're solving for V? We're solving for the amount. Huh? No, what we're doing is we're solving for V in this equation right here. Because what I'm trying to do is I'm trying to calculate this voltage right here. If I can calculate that voltage right there, then I can figure out how much voltage I'm going to get out of this. So as soon as I had that filter, this 2V peak over pi, this is gone. As soon as I had that filter for a half wave, that V peak over pi is gone. This only works if the thing pulses to ground, right? You understand that? That's the DC average of an alternation. Well, we don't even have an alternation anymore. We got DC. But I'm trying to figure out how much DC do I have? Well, the only difference between here, this is VP, and here is the amount of this ripple voltage. So if I can calculate the amount of ripple voltage, then by George, I can figure out exactly what I'm going to get out of this power supply. And then I can transpose it and solve for a capacitor. So if I'm solving for my power, if I'm saying, okay, What size capacitor do I need to limit my ripple voltage to 1 volt peak to peak? Well, that's going to be determined by the current, right, and the size of the capacitor. Does that make sense? So what we're trying to do is we're going to look, and this is not that complicated. People think designing these power supplies is hard, but these guys are not hard. All you got to do is say, okay, I need 5 volts. What size transformer? What size standard transformer am I going to get 5 volts? Well, odds are you're going to use like a 6.3 volt transformer, right? You understand that? Then you got to say, okay, what diodes am I going to use? Well, I gotta buy a diode that has a reverse breakover voltage that will block peak. By the way, when you put a capacitor on there, they got to block peak to peak, because when it goes this way, your capacitor's charged up the other way. So that means if I've got 100 volts peak to peak, then the breakover voltage on my diode is going to be 200 volts, at least, right? Y'all follow me so far? And what current? Well, if my load needs 5 amps, then I got to have a diode that has an IF of at least what? Of at least 5 amps. And usually we would make it, we'd increase that about 50% to make sure the diodes were able to handle other situations. Then we can say, okay, well, how much DC do I need to get out? Well, the DC is going to be determined by that ripple voltage right there. And the only difference between V peak, so now we're going to deal with V peak. We're not going to deal with 2 V peak over pi, because we're not, this is not an alternation anymore. We're not pulsating this DC anymore. This is DC. Y'all understand that? So all we're doing is we got this formula up here, and we're trying to solve for V. No, we're going to use this equation right here. Everything we need to know is in that equation right there. All I'm going to do is rearrange that equation to solve for V. Let's work it this way and see if it makes a little more sense. So let's go ahead and move R over to that side. So if I've got T is equal to R times C, then R would be equal to T over C. So we can come over here, now we can come over here and we can say V over I is equal to T over C. So what's nice about this way, it's real easy. If I leave V up here and I come over here and move I on this side, all we do is just pop it up there, right? So now we say V is equal to I times T over C. So that was a lot easier than trying to do it that way, right? So what's V equal to? So V, and this is ripple peak to peak, is equal to what? I times T over C. Now C is the size of the capacitor in farads. I is the current required by the load. And then T is the time for the pulses, which we call the period. So that means if I'm running a 2 amp load and I'm using a 10,000 microfarad capacitor, then my V ripple peak to peak would be equal to 2 amps times half wave or full wave. Full wave. So I would say 8.3 milli, and I'm using what I say a 5,000 microfarad capacitor. By the way, capacitors do not use legal engineer notation. We basically rate, capacitors are basically bought in two ranges, microfarads or picofarads. So we'll have 100,000 microfarad capacitor. So, but you got to enter that in. So how would we enter that? We'd say our V ripple peak P would be equal to 2 amps times what? 0.0083, but we would just enter it in engineering notation, and then 5,000 micro. So what would be my voltage? 8.3 milli, 2 divided by 5,000, and that would be my ripple voltage. Where did the 8.3 come from? That's exactly the period of a full wave. If you bring 60 cycle in, then what happens is that with full wave you get twice the frequency out, right? Y'all understand that? So if I bring 60 cycle in, then I get 120 cycles out. And 120, if you take the reciprocal of 120, it's going to be 8.3 milliseconds. If it was full wave, then I would use 16.7 milliseconds. So my V ripple peak to peak would be what? 3.3. So that means from the bottom of this trough to the V peak right here, or V peak out, that would be the amount of ripple voltage I have. Now, if this was sitting at 40 volts peak, what would be my measured output voltage? So what's my device going to do with this right here? What's the DC average of a sine wave, of a cycle? What's the DC average of a cycle? What's the DC average of a cycle? 0. Y'all understand that? That's a very important thing, and for some reason, people get this 2 dB over pi, 0.667 on there. So I guarantee on a class even this size, I can put what's the DC average of a cycle, and I can put 0.637 down there, and somebody in this class is going to choose that. That's not the average of a cycle, that's the average of an alternation. Right? You understand that? But I guarantee, Courtney said that's probably going to be big. We'll see. We'll see. Even a class this small, and that's going to be on the test, by the way. I think it probably on the first test. So what I would do, if this was 40 volts, what your load is going to do is it's going to average this thing out right down the center. So see, my DC average is going to be somewhere down there. So if you look at your formula sheet, it says that my DC average would be equal to V peak. So my DC now is going to be equal to V peak out minus V ripple peak peak divided by 2. That's the formula. Another thing you can do, though, to makes it a little easier, is that, so right now, you would have to know that a full wave on 60 hertz, the full wave time would be 8.3 milliseconds. And this would be full wave. And then half wave, it would be what? 16.7 milliseconds. You say, well, if I double 8.3, I don't get 16.7, but it's actually, it's 8.3 is It's 8.333333, and it's 16.666666 is what it actually is. But the problem is, what would it be if my AC coming in was 400 hertz? Well, now keeping these two numbers in your head don't make sense. So now I'd have to use my calculator to find the period before I can do that. So the formula, period is equal to 1 over frequency. So what we're saying is I can come up here and rearrange this format 1 over frequency. So, and time is equal to 1 over frequency. So if time is equal to 1 over frequency, it means I can substitute 1 over frequency in that equation, right? Y'all understand that? So we can come up here and redo the equation just a little bit, where we say, this is on your formula sheet too, V ripple peak is equal to I over C times L. And this is the one I like to use. So if my input frequency is 60 cycles, then for full wave I would use 120, and for half wave I would use 60. If it's 400 cycles, for full wave I would use 800, and half wave I would use 400, right? Y'all understand that? So your ripple frequency is, for full wave, is twice your input frequency, and for half wave it's equal to your input frequency. So now I don't have to do that. This is, to me, this is easy. So what's I? This is the what? The load current, right? What's C? And when we say size, we're not talking about the physical size. We're talking about the farad size, right? And farad should be capitalized because it's somebody's name. And then what's L? Of the pulsating DC. But if the load current goes down, the ripple voltage goes down. If the load current goes up, ripple voltage goes up. So your DC output would vary with load. If your DC output varies with load, then it's not regular, which is really good. So I could rearrange the formula and solve for C. So if I was designing I would say, okay, I can afford to have this much ripple voltage. So what's nice about, if it's on the bottom over here, on the top over there, you just swap them. So what would C be equal to? So all I have to do is just swap them. So C would be equal to IT over what ripple voltage I was trying to get. And you would always take the capacitor up to the next standard size, even if it came right on top of it. So I was trying to design a power supply, and I said, well, I can afford this much ripple voltage. My load's going to need this current. It's going to be a full wave rectifier, and then you can stop and see. And then we'll show you later on how to add the regulator. So this is a filter. Y'all go ahead and take a break, and I'll show y'all the video when y'all get back, and then we'll look at lab. If I can find it. This is blowing up capacitor. on purpose. We so y'all gonna do this on purpose. We used to have a three-phase. The way we used to teach motor controls here, before we got our motor controls trainers, we had these panels that had three phases up there, and that was the guy in there taking these electrical capacitors across 208 three-phase. Yeah, going over there, but the breaker for turning on the three-phase was right up above, so he was leaning over to turn that thing on. Yeah, Steve, I forgot his last name. We used to teach classes up in 250, and it was an old physics run, but they wasn't using it. So that's where we did all our microprocessors and everything. And they had gas on the bench before we had it turned off. And I was coming down the hall, I heard oh, and Steve, same guy, was in there with a cigarette lighter under that gas valve. Like a what? You probably, I don't know. Big thing. We used to make cables. We used to make them out of cans before they came out with PVC pipe. And we did a bunch of aluminum cans and tape them together. Put a little lighter plug in there and shake it up real good to make it turn into a gas and stick something in the end. Or you can launch stuff. Now they use PVC pipe. Yeah, this. Well, but you got to understand, these cans wasn't made out of them. I was in the tin can. So you had huh? Yeah, those have been around a long time. The tops were aluminum, but the can itself was made out of tin. For tin cans, everything's glass. You bought everything in glass bottles. Like all these drinks and everything, was mostly stainless steel drinks. And they came up with tin cans with metal. They still make those. And then the drink cans were tin cans, but they had aluminum tops on them. You just cut the aluminum tops out of them and take. I know I use nice PVC pipe and making expansion chamber back there. squirt something in there that's explosive, put your potato in the other end. They use these piezoelectric igniters too, like you buy for your grill. You buy them in Lowe's, and they stick those things up in there, so they got a trick. Pop them so you don't use cigarette lighters. They ever make a potato in it? Oh, really? Yeah, I had a friend of mine had a flare gun. And he figured out a 12 gauge shotgun shell was fitted in his flare gun. That it went off, but he only did it once. But he put all this stuff around his arm. It was so funny in case it did blow up. It shot, but it didn't blow up on him. But that was the last time he did it. Just the recoil on it, trying to hold it with your hand. You can't hardly hold a shotgun like this, like they do on TV. They'll have these sawed-off shotguns, and they'll have it up there on one hand like that. They what? Yeah, I saw one where a girl was shooting a shotgun. It knocked her. But yeah. So guys,